Hello, and welcome back to the course. So today we're looking at holomorphic functions defined by integrals. So either integrating out a variable or integrating a function against some kernel, like, for example, the Cauchy integral formula. This would be one example of that. So this is subsection 3.4.1 in the book. All right, so suppose that you have an open set U, and you have a function C, which is a function of two variables, z and t. So the z is going to vary in the U, and the t varies in the unit interval. It could be any sort of interval, really. And let's suppose that that's a continuous function. So a continuous function as a function of both variables. So as a function of z and t, right? So really maybe as a function of three real variables, x, y, and t, if you want to think of it that way. And such that for any fixed t, so if you fix a t and you just look at the function as a function of z alone, that function is holomorphic. All right? Then, given this, then we have that if I integrate out the t, so if I integrate from 0 to 1, where this t is defined, this function c, then I get a function of z alone. There's no more t, and that is a holomorphic function in U. All right. So there's really two common ways of proving this, because for holomorphic functions, it's basically functions are holomorphic if they either, you can think of them as satisfying a certain differential equation, which is sort of the common way of thinking about it, or it's actually they satisfy a certain integral equation using Morera. So it turns out using Morera is actually a little bit simpler. So we'll use both of these both of these results to prove this lemma. So we'll give both proofs, and Morera is actually easier here, right? And so with Morera, we're actually we're using Fubini to there's going to be to prove a result like this, you have to switch the order of some limits. So in this case, the order that we're switching is we're switching to integrals. So Fubini is the thing that we're using here. All right. So let t be a triangle, solid triangle in U, any solid triangle in U. Well, let's integrate over the boundary of this triangle. Right? We're trying to show that given any triangle in U, that this guy is 0, and then we can apply Morera to tell us that this function is holomorphic. All right. So, well, let's put in the definition of h, right? It's this integral. So that's this guy over here. And now let's apply Fubini, right? And so we swap the order of these two integrals, right? And so now this dz is inside, and now you look at this inside integral and notice that, well, when you're doing that integral, you're really doing it for any fixed t, right? So now over there, you can just apply Cauchy-Transform. Really, we're talking about triangles, right? So it's just whatever is inside here, that's just 0. So we're integrating 0 from 0 to 1. That's always 0, right? So therefore, this guy is 0, and and we'll get we can apply Morera. Now, why were we able to apply Fabini? Because you can't always swap, two integrals. But in this case, you have, if you think of this integral over here, I mean, if you think back to Fabini, just the standard Fabini that you see, it's always an integral over two subsets of the of the real line, or maybe well, it depends on which Fabini, which version of Fabini you're looking at. But it's usually, like if it's the two-dimensional one, it's some interval and some other interval, right? And so when you're doing those, if you're using the like for example here, we could just use the Riemann integral. So that version of Fabini will work if your function is continuous, and it is. In this case, it is continuous. It's continuous on this integral on this triangle, right? And what is the triangle, right? Each leg separately is really an integral over an interval, right? So it's really it's three calculus 1 integrals, right? So the standard Fubini theorem for Riemann integrals applies. And if the measure theoretic version applies as well, right? In this case, it would be even easier. You don't even necessarily need continuous. You could get by with something weaker. You could as long as you'd have you'd have to have some integrability, right? But in this case, we're fine. It's a continuous function. So, all right. So now we apply Morera, and we get that H is holomorphic, right? So that's proof A. That's the easier proof. That's the one that you don't have to check too much for. But there is a second proof, which is actually the one that I would probably think of first, even though it's slightly more complicated. But it's maybe the one that looks more like a whole bunch of other similar proofs. Basically, if we're thinking of holomorphic functions as solutions of a certain PDE, and you're integrating, something which satisfies that PDE in some variables, then the integral, the function that you get out of the integral still satisfies that PDE. So that's a fairly common thing to do, and it requires the switch of limiting operation that we need to do here is as we need to bring a derivative underneath the integral, right? So we're using the Wertinger derivatives here because we're going to be applying, we're basically trying to do the Cauchy-Riemann equations, and so I'm writing them as using the Wertinger derivative, so the z-bar derivative. We're basically, again, trying to show that this guy is 0, right? Now let's write down what that is. So I have, that's just h of z, and I'm trying to differentiate that with respect to z bar. So using the Wertinger derivatives, right? Again, these are derivatives in x and y somehow combined together, right? All right. So if I switch the order of these operations, let's worry about that in a little bit. Why we can do that? If I move that inside, then well, what do I have inside here, right? I mean, t is fixed, and I'm differentiating with respect to z bar. That function is holomorphic. For each fixed t, that's a holomorphic function, so the z bar derivative is just 0. So again, I get 0, right? All right, so what we're really doing is passing the x and the y derivatives underneath the underneath the integral. So we're using the Leibniz integral rule really for passing, differentiating underneath the integral, and we're doing the actual derivatives that we're doing is the x and the y derivative, right? Those are the ones that we're passing underneath, right? There is no such thing as a z bar derivative, really. Here that's the Wirtinger operator, right? It's this operator, right? That's what we're doing. So it's not an actual derivative. It's constructed out of actual derivatives, right? And we apply the Leibniz integral rule, and we presumably get the result. Okay, well, could we apply the Leibniz rule? So can we pass underneath? Well, we didn't really assume everything that Leibniz required. So Leibniz required something about the derivatives, right? And while we only assumed that that this guy is holomorphic as a function of z, but we didn't really say anything about, well, what about the x and the y derivatives, right? We didn't really assume that these, if I take the x derivative of c, well, that's supposed to be, if I'm in what standard Leibniz needs, it needs to be a continuous function. Not just a continuous function of x and y, it actually needs to be a continuous function of x, y, and t, right? Or of z and t, right? It needs to be, I need a continuously differentiable function, right? So that's not quite what I asked for, right? Well, in what we assumed in the lemma, in the hypothesis. So if we did assume it, if we added that extra assumption, then yeah, well, this would work. But we actually had an exercise. So if you have this condition that this guy is holomorphic for each fixed t, then and the function c is continuous, then this was an exercise that I talked about before. You actually do get that these guys are continuous functions of all the variables, and that follows from writing down the derivative using the Cauchy integral formula, right? So, and integrals are nice about continuous functions. Derivatives are terrible. Integrals are nice, right? So, because we had the Cauchy integral formula for the derivatives, we actually get that here. We do get C1, which is what we needed, right? Okay, so then we're done. We get a nice, everything's nice, continuously differentiable function, and satisfying the Cauchy-Riemann equations. We were allowed to swap these two operations, right? And we're done. Cool. All right. So let's write down a quick corollary. So, it didn't have to be 0 to 1. Something that actually comes up often in one variable complex analysis, as we've clearly seen, is integrating over a path, right? And so this could really be a path or a chain in this case, right? So so you could have a chain, right? Chain is just going to be this integral is just a sum of a bunch of path integrals, and each one of those path integrals, when you parameterize it, is really an integral from 0 to 1. You could always parameterize that way, right? So therefore, if I have a continuous function such that for any point on the path, right? I have that the C is a holomorphic function, right? So I have a function on U cross a path, right? So a function of really, two variables Z and W, but the W only has to range over the path or over the chain, right? Then I have, again, if I integrate it out, I get a holomorphic function, right? So, for example, one place where we've seen this is in the Cauchy integral formula. So we could, if we have any continuous function f defined on a circle, right? Any continuous function, we could define the so-called Koshy transform, which is basically something that eats continuous functions on the circle and gives us functions defined on the disk. And the way it does this is that, say, well, what is CF at Z? Well, we just write down this formula. And so basically, in terms of this corollary that we see here, that the C is this guy inside, well, that's a continuous function on this disk, right? That's where Z lives, right? Well, actually, I mean, it's going to be continuous in a large set, but definitely in the Z. And it's also another the other variable is the so I have Z and W, right? W, that's the zeta here, right? That's the thing that I'm integrating against, right? So that really, I'm only looking at that, that doing something on the path, right? So this is actually continuous because zeta minus Z is never zero because Z is in the disk and zeta is on the boundary, right? So this thing is, that does the right thing, right? And so I get a function defined out of it. And one thing that, if I apply this corollary, I get a corollary. So one thing that we get out of this is that, that the lemma proves is that this CF is a holomorphic function. So the Cauchy transform is a holomorphic function. So it's a specific application of this corollary, right? Specifically to this guy. All right. Now, one thing, if we're going to apply this, I mean, it seems like, well, we can start with any continuous function on a circle and define a holomorphic function inside. You have to be a little careful, though. I mean, this Cauchy transform, yeah, I mean, it's defined for any continuous data on the boundary, but it's not necessarily going to be that f is going to be the boundary values of CF. If I look at what CF does, it's not necessarily going to go. If I look at CF of Z and Z approaches a point on the circle, on this guy, it's not necessarily gonna approach the value of f there, right? It might almost have nothing to do with it, right? It might be a very, very different function. Even if it exists, it might not even exist, right? That limit might not exist, right? All right. So one other thing that we get out of it, which is maybe not as as exciting as it seems, but we get a converse to Cauchy's formula. So Cauchy's formula is really an if and only if, right? That if we start with a continuous function and on the closed disk, right, on the entire closed disk, and we get that the Cauchy formula is satisfied. So this is true for all Z inside, right? Then f restricted to the inside is holomorphic. Well, why? Well, we get that this guy, that's just the Koshy transform of little f restricted to the boundary, right? So that guy is holomorphic, right? And now we say, well, but we're assuming that equals f. Yeah. So then we get that is holomorphic. So Cauchy's formula is really an if and only if, right? If Cauchy's formula works, then you get a holomorphic function. That's not really that exciting, but yeah, that's basically what we prove, right? All right. So next time we're gonna look at convergence of holomorphic functions. So if you have a sequence of holomorphic functions, what do we want the convergence to be, right? If you really want, anytime that you have some class of functions, you want to ask, well, what is the right topology? When do things converge? And what's the right convergence for this class? And so that's what we're gonna look at next time. All right, so see you then.